Hello everyone, welcome back to the channel. So today we're going to look at an interesting question. Of course, it's not simple harmonic motion. We've actually officially ended the simple harmonic motion series. I hope you enjoyed the season and you learned something new. And today we'll be looking at a question from 9702, June 2003, paper 4. So don't ask me why I went all the way back to 2003, that's like 22 years ago. I just suddenly went to this particular year and I clicked on the paper and I saw a very interesting question. So I was like, you know what, this is worth discussing. So here we are. And we're actually looking at question 2B. I'm going to skip A because A is actually a simple question. So let's go with B. So this question, to me, I find it a bit crazy. But if you understand what the question is actually asking, then you'll be able to solve it. So without further ado, let's get started. Alright. A jeweler wishes to harden a sample of pure gold by mixing it with some silver so that the mixture contains 5% silver by weight. Okay. The jeweler melts some pure gold and then adds the correct weight of silver. The initial temperature of the silver is 27 degrees Celsius. Use the data of figure 2.2 to calculate the initial temperature of the pure gold so that the final mixture is at the melting point of pure gold. Okay, so this 5 lines of sentences actually has a lot of information. First things first is the mixture contains 5% silver by weight. That means it contains 5% silver by weight, that means it contains 5% silver by mass as well. Because W equals to mg and W is proportional to m, right? So if 5% by weight, it should be 5% of mass as well. But we don't know what's a mass. So that means we're going to let it to be m, for example. Then they say he melts some pure gold. That means he melts the gold. And then he add the correct weight of silver. Okay, then the initial temperature of the silver is 27 degrees Celsius. Use the data in the table here to calculate the initial temperature of pure gold. That is the question. So that the final mixture is at the melting point of pure gold. So if we were to look at it like this, we have gold, we have silver, right? So initial temperature I denote as IT, okay? Initial temperature of gold is what we're going to find, so I'm going to put it as X. Silver is 27 degrees Celsius and in Kelvin it is 300. Why I'm putting it in Kelvin? Because if you look at the table, all of the units are in Kelvin. So I'm going to change my temperature also in Kelvin. Another thing to note is your units. This specific heat capacity is in joule. Specific latent heat of fusion is kilojoule. So if let's say you were to use specific latent heat of fusion later, make sure you convert your kilojoule to joule. That means make sure you times 10 to the power of 3. Okay, now coming back. So we know our initial temperature for silver is 27 degrees Celsius and we have converted to Kelvin, which is 300 K. Basically, you plus 273. Okay. Then the final temperature for both is the same, which is 1340 Kelvin. Now why is 1340? Because they did say the final mixture is at the melting point of pure gold. And based on the table here, the melting point of pure gold is 1340. So that means the final temperature has to be 1340. And it's a mixture, so both of them has the same final temperature. So from this table itself, if you didn't realize, this is actually a thermal equilibrium question. Why did I conclude that? Because the final temperature is the same. When, for example, two objects that are in contact, let's say you have object A and object B. Okay, so you have object A and object B. they have both objects are in contact, and both of them has their respective temperature. Let's say this is 27 degrees and this is what, like 50 degrees Celsius. What happens is there will be heat transfer, right? They will keep transferring heat. One will be releasing heat, one will be absorbing the heat. So this process will continue until there is no net heat transfer. Until there's no net heat transfer and the temperature will be the same. This is basically how thermal equilibrium works, right? Same temperature, they'll reach the same temperature and there'll be no net heat transfer. That means the heat gain is equal to the heat loss. That is what they mean by no net heat transfer. There is heat transfer, but no net. So the important keyword here is net. Net, as in when you add your heat loss and your heat gain, you'll get 0. So same thing here, but now it's not, of course, not object A and B. Instead, it's now gold and silver. Okay. So now the question is, who is absorbing heat? Who is releasing heat? Is it gold that absorbs heat? Is it silver that absorbs? Or do they release heat? Who does what? So to know that, we need to look at their phase change. Or in other words, you can also look at the temperature change also. So let's start with silver. Since we have more information on the silver, right? We have the initial temperature and the final temperature of silver. So let's put silver here. So, speaking of phase change, do you think that initially the silver was a solid or is the silver liquid? I mean, no way it's a gas, right? So it's either these two, solid or liquid. And the answer is solid. Why is it solid? Because initially, silver has a temperature of 300 Kelvin. And if you look at the table given here, which is figure 2.2, silver has a melting point of 1240 Kelvin. So looking at the number itself, 300 Kelvin is definitely less than 1240 Kelvin. So that means the silver hasn't reached its melting point yet. That means it is still at solid. Therefore, the first stage of silver, initially, it is at solid. And it is at 300 Kelvin. And now, remember the question said here, the final mixture is at the melting point of pure gold. Both of them has a final temperature of 1340. That means the ending temperature, the final temperature of silver must be 1340 Kelvin. So there is a process that it has to go through. There's a few phases that it has to go through until it reaches 1340 Kelvin. So just by looking at the temperature itself, the temperature increases. That means silver is the one that is absorbing heat. So when you write your equation, it will be heat absorbed. So if silver is the one that is absorbing heat, gold is supposed to be releasing the heat. Or you want to say gold undergoes heat loss. Okay, we'll go to the gold later. Let's finish silver first. So first, it started at solid, 300 Kelvin. Then, of course, it increases its temperature. It reaches its own melting point, which is 1240 Kelvin. Of course, same phase. Still the same phase, just that temperature change. This is where specific heat capacity comes in. And we call this as, is where you put your formula M. That is very big. Let me make it smaller. MC theta. Right. Same phase, but different temperature. And after this, what happened? It has already hit the melting point. And this is where you have a change in phase, but no temperature change. And this is what we call as specific latent heat of fusion. Still 1240 Kelvin, but got phase change. And this would be ML. Then, already hit 1240. Now increase its temperature again to 1340 Kelvin. Still in liquid, of course. So temperature is changing, same phase, MC theta, specific heat capacity. So easier way to look at this is using a graph. So let me draw a graph for you. So this is the graph, and your x-axis would be energy supplied or heat energy added. I think I'll better put heat energy. Yep. And your y-axis would be your temperature. Okay, so initially silver was a solid here, right? So 300 Kelvin is somewhere here. Okay, then it reaches its melting point 1240 Kelvin. How I know it's melting point? Because they already give here. The melting point of silver is 1240. Okay, after it reaches its melting point, then there is no increase in temperature or decrease in temperature, just phase change where the solid changes to liquid. Then it increases until 1340 Kelvin. So the phase change is here is solid, here is solid to liquid, then liquid. Easier to see using graph, right? Yep. So you need to be careful to use which formula at which part. Remember, when there's no change in phase but there's a change in temperature, that is specific heat capacity. And when there is change in phase like this but no change in temperature, then it's specific latent heat of fusion. In this case it's fusion because it involves solid and liquid. So if you get confused usually which to use, always draw the graph so you know when there's a change in temperature and when there isn't change in temperature. Okay, so now let's calculate our silver for heat absorbed. Okay, so for heat absorbed, Q, or you can just put your Q is the what we call the symbol for heat, right? Heat energy. MC theta plus ML plus MC theta. Right? This is what we have based on what you have drawn here. You can factorize your M out. M, which will give you C theta plus ML plus C theta. Okay. Also, the theta here and here are not the same, okay? So maybe you can put X, Y, so that you don't accidentally plus C theta plus C theta. Yeah, it's not the same temperature change. So what is our mass? Our mass is actually 0.05 m. Why? Because in the question, they did say 5% silver by weight. So we know W is equals to mg, and of course W is proportional to m. Therefore, if it's 5% of silver by weight, it should also be 5% of silver by mass. But we don't know what's the actual value of the mass, so we're going to denote that as m. So it is 0.05 m. Okay, now let's sub in our value. Specific heat capacity for silver is 235. Check unit is in joule. Okay, good to go. 235. And the temperature change is 100, not 100. I keep saying 100. 1240 minus 300. Remember, Kelvin. Check your unit always. Then, plus, what is your... I just realized I added my m here. I already factor the m when I go and edit again. It's just latent heat, okay? Yeah. Plus, L is 600, not 600, 105 for silver. Times 10 to the power of 3. Why I times 10 to the power of 3? Because it's in kilojoule. And make sure you take the silver one, okay? Then, plus 235 again, specific heat capacity. Temperature change is 1340 minus 1240. There's a very big, there's a lot of numbers here, so when you put it in your calculator, make sure you put it properly. Don't put it too fast. And this would give me, okay, wait, let me write my 0.05 m. This will give me 11045 plus 105 times 10 to the power of 3 plus 23500. And I will get 17470 M. So you'll get it in terms of M because you have your M here. So that is for silver. So therefore, from what we have discussed, silver is the one that's absorbing heat. Now let's move on to gold. So if silver is the one that's absorbing heat, someone's got to lose them, which is the gold. So gold will undergo heat loss, Q. So now what would be the phase for gold? So they did say here, the jeweler melts some pure gold, then only he add the correct weight of silver. That means the gold is already molten. So if I were to draw a picture here, this is the container. This guy has already melted the gold, so it's already melted gold here. This is, or you can say, molten gold. Then after the gold is already melted, like the melted gold, then he add in the silver. So the silver came in contact with the gold when the gold is already molten. So our phase change should start when the gold is at molten, or when melted, the gold is already melted. So it should be liquid. Okay, let me erase this. I write down here. Should be liquid. Right. So this is what we're going to find. What was the initial temperature when the guy added the silver? What was the initial temperature of this gold when the guy added the silver in? We know the final temperature. The final temperature is actually 1340 Kelvin. Right, because they did say here, final mixtures at the melting point of pure gold. Yes, 1340. So in order for the gold to lose heat, to release heat or lose heat so that the silver can absorb, the gold has to cool down. That means X, or you can put as T, your initial temperature of gold must be greater than 1340 Kelvin, because it's cooling down. When you're cooling down, you release heat. When you release heat, the silver will start to absorb heat and increase its temperature until 1340 Kelvin. So same phase, different temperature, and this is MC theta. Therefore, if we were to write the equation, heat loss by the gold, of course, is MC theta, and your M is 0.95 M. Why? Because 5% silver by weight. Therefore, the rest 95% is for gold. That's why it's 0.95, and also it's M, because you don't know what's the actual mass. Okay. Then your specific capacity is 129, and it is X minus 1340. And therefore, you will get 122.5 M X minus 1340. Let me just double check this. Wait, 0.95. Actually, it's 122.55. Better put both decimals. 2 decimal place. Then you get a better answer. Okay. So we've got our heat loss equation. We got our heat absorbed. So coming back to the fundamentals of thermal equilibrium, where when both of them reach thermal equilibrium, they hit the same temperature. There is no net heat transfer. That means the heat absorbed and the heat loss are equal. So if I were to write the equation again, heat loss equals to heat gain. So your heat loss equation is 122.5 0.55 m x minus 1340 equals to 17470. 174, okay, I should change my color already. Yeah. Okay, you know what? Wait. Let me write this at the side here. Heat loss equals to heat gain. So heat loss was 122.55 m x minus 1340. Your heat gain was 17470 m, right? Yep. Your m you can cut, then you do your math. You'll get your x as 1483 Kelvin. If you want to put to two significant figure, it's 1500 Kelvin. If you want to put to three significant figure, it's 1480 Kelvin. And this is your answer. Yep, so that is the initial temperature. And like I said, it is more than 1483 is more than the final temperature because it is cooling down. So actually there's a few things to actually be aware in this question. So I had these questions myself when I was doing this particular question. Yeah, so I had a question for the question itself. I was just curious if it is possible to work it out that way. So first things first was, is it possible for the gold to solidify? That means the liquid becomes solid. Can this happen in this case of scenario based on the question? Unfortunately, no. Because the question explicitly mentioned that the final mixture is at the melting point of the pure gold. I mean, the final temperature of the system is actually 1340 Kelvin. If let's say it started to solidify, it would release extra latent heat. Why latent heat? Because different phase, right? And they are in the same temperature. Definitely this is also 1340K, definitely. But if it did start to solidify, like I said, it would release extra latent heat. When it releases extra latent heat, so what's the problem if it releases extra latent heat? So gold release the heat. Who is going to absorb it? Silver. Right. So if the gold release extra latent heat, that would hit the silver beyond 1340 Kelvin. Because the silver is going to absorb the extra heat, and which contradicts the conditions in the question. The question explicitly mentioned at the melting point of pure gold. So the gold just cools to 1240 Kelvin exactly at its melting point and stops there, still molten. It will not go further to solid, it will not solidify further, because if it goes further, it releases extra heat. Therefore, silver has to absorb extra heat and the temperature will go beyond 1240 Kelvin, which is not what the question wants. So that's why gold will not solidify. It will just maintain as molten. That is one thing I had in mind. Another thing is it possible if I say, okay, before even I ask if it's possible, let me draw the graph first. This is temperature, this is energy. This is basically X, which is the 1438 Kelvin, and this is the melting point of gold, is 1340. So what happened was the gold cools down to this melting point, right? And then reaches the 1340 temperature together with silver, and there's no net heat transfer anymore. Okay. So I had a question. Why didn't we include this front part in the calculation? As in, why didn't we include the part where, how do I know that, I only start from liquid? Why can't I start from solid? Like I started silver from solid here, right? Here I started from solid because it is less than the temperature at the melting point of silver, so I know that the silver is in solid. But here I don't really know, so there's a possibility I can say that, why can't I take into consideration of solid here? Why can't I just go through the process here then go up. After that, I say, okay, now it cools down. So why not I add solid to solid, then to liquid. After that, it cools down. Why is that not possible? So that is not possible because, first of all, one thing that I realized was the question explicitly mentioned the jeweler melts some pure gold, and then he said, and then he add correct weight of silver. That means he has already melted the gold. The gold is already molten. Then only he added silver. So the process begin at this point when this gold is already in molten. When the gold is already in molten, then only he added silver. And in order to achieve thermal equilibrium, gold cools down to release heat, and silver absorbs the heat from the gold. Right? So the front part, you don't have to take into consideration. So that's all for today's video. I hope you actually understand. It's okay if you still haven't understand. Take your time, rewatch the part you don't understand, slowly digest it. This question is actually a little bit crazy, not gonna lie. It's a bit insane, but if you can analyze the question and stay calm and actually understand what they're trying to say, you'll be able to do it. You can also draw graphs like this in exam, because I feel like it might be useful in knowing whether to use MC theta or ML, and to know the temperature change. Yeah, so that's all for today's video. Thank you for watching, and I'll see you in the next one. Bye bye, have a nice day, and remember to stay hydrated. Drink a lot of water, it's so hot these days. Okay, bye bye.